Right. So what we have discussed so far is under the logic gates, we discussed the three basic, we discussed four basic logic gates, that is O, N, and NOT, and exclusively OK. From previous, we discussed the outcome of O gate is whenever the one of the input is 1, the outcome is 1. So symbol is something like this, and we call this as, if the inputs are A and B, the outputs F. F is equal to A plus B. This plus means Boolean addition. So Boolean addition means not really mathematical addition. So you see that we know we have binary digits. So when you say 0 plus 0, it's 0, 0 plus 1, it's 1, 1 plus 0 is 1. Okay, remember this is careful. 1 plus 1 is also 1, which means this is operation. Similarly, we discuss AND gate as well. What you need to remember about the AND gate is the output is 1 whenever both the inputs are 1, right? Or you may say all the inputs are 1. So the symbol is this, and if the inputs are A and B and output is F, so mathematical Boolean expression we can write like F equals A dot B. That means Boolean multiplication. So similarly, we can have the binary representations. 0 into 0 dot 0 is 0, 0 dot 1 is 0, 1 dot 0 is 0, and 1 dot 1 is 1. Right. Then the third one, we discuss NOT gate. We know NOT means complement, which means if the input is A, the output will be complement of A. That means we call A bar, or we sometimes say A dash. So the NOT gate, we have A and the outcome is F, right? So that means if we can say that it's a complement of A, or we can represent it as A bar or A dash. So when you say 0 bar, that is 1, A bar, that is 0. So the fourth one, this is new, is exclusively O. Symbol is similar to this one. If the inputs are A, B, and the outcome is F, in the truth table, we can see that it's exclusively O means whenever one of the input is 1, then only the output is 1. So you see that apart from the O gate, we have, when you have both inputs are 1, the outcome is 0 here. So Boolean expression we put like this, A plus with a circle, B. Actually, this is similar to say that F is equal to A bar dot B plus A dot B bar. So we have drawn a truth table to identify this. So when you actually draw the truth table, you will see that outcome of F is similar to the outcome of exclusively OK. Combinational gates. That means when you made up these 4 logic gates together, we can create more gates. For example, NAND gate, NOR gate, and exclusively NOT gate. NAND gate, we know it's a NOT and AND gate, and symbol is similar to this one. And the Boolean expression is A dot bar, A dot B bar, or A dot B dash, right? So the what you need to remember is outcome is 1 whenever the inputs are not, all the inputs are not equal to 1. Or you can say that if one of the inputs, 0, then you can say the outcome is 1. Similarly, NOR gate means not plus O gate. and the symbol is similar to this, and the Boolean expression is A plus B bar. And then the truth table gives you whenever the output is 1, when all the inputs are 0. That's all what you need to remember about no key. New to this exclusively no gate, that means XO plus not gate. So the symbol is similar to this one. We know exclusive OR gate is whenever one of the input is 1, the output is 1. This is the complement, opposite. So whenever the input is one of the input, only one of the input is 1, then you have outcome of 1. So which means you can say if the inputs are both 0 or 1, then you can say outcome is 1. So the Boolean expression F equals A plus with a circle B bar, which will give you the Boolean expression for X no gate. We did a couple of exercises on given a logic circuit. We asked to draw the circuit, we'll come up with a Boolean expression and draw the truth table. The new thing that we have discussed last time, this is where we did work on last time. We discussed something called universal gate. The term universal means using universal gate, you can create any other gate. Right. So there are two universal gates we are going to learn, NAND and NOR gate, which means using NOR gate or NAND gate, you can create any other gate. So the first thing that we have discussed last time is implementing a NOT gate using NAND gate. So what you do is actually you get a NAND gate and you short circuit this. Short circuit means the input, we have a single input A, which means the second input is or connects to the first one, which we call short circuit. So when you short circuit it, we know that Q will be A dot A bar, right? A dot A bar. So if you look at this, what this A dot A bar is, if you draw the truth table, we know for A, we can get 0 and 1. Multiplication of A with A will be 0 and 1. Complement will be 1 and 0, which means not gate. So we can say that when you short circuit a NAND gate, we'll get a NOT gate. Mavina, is it clear?
Yes.
Right. Now, the next thing that we are going to use AND gate. Now, when you have a NAND gate, how do you make it an AND gate? So to implement AND gate using NAND gate, we are using two NAND gates. First NAND gate, we know that when you get this, you will get A dot B bar. And then we put a NOT here, right? You short circuit this. So basically this NAND gate acts as a NOT gate. When you look at the expression, you will get A dot B bar into A dot B bar bar. If you write the truth table, now you see that this is similar to AND gate. I think logic is understandable. We have a NAND gate, we put a NOT gate. For that, we get another NAND gate, we short circuit it. And at the end of the day, we are getting, right, AND gate. Right, good. Third one, OR gate. To create an OR gate using NAND gate, we need 3 NAND gates. What we do is we provide A bar, B bar to a NAND gate. Now to get the complement of A, we will get NOT gate, which means we get a NAND gate, we short circuit it. We'll get B, again short circuiting, and Q will be A bar dot B bar bar. And if you look at the truth table, this is similar to O gate. ඒ කියන්නේ O gate එකක් හදන්න නම් අපි NAND gate තුනක් ගන්නවා. අපි කරන්නේ NAND gate එකකට දෙනවා input එකේ complement එක. ඒ කියන්නේ දෙකේම complement එක දෙන්න අපි තව NAND gate එකක් දෙනවා short circuit කරලා. මම ඉන්නේ පැහැදිලිද පුතේ? If it is not clear, I will take you some other time and we'll discuss it again, right? You have to do this by your own to understand this. Similarly, we can do the same with the NOR gate, right? So to create a NOT gate, you short circuit it similar to the previous one. We'll get A plus A bar, which is similar to NOT gate. And similar to O gate, using NOR gate, we know that you have to add a NOT gate, which means using two NOR gates, right? Using two NOR gates, we can create a O gate. And similarly, what is not here? Right, right. So let me quickly do this for you, right? Right now, what I'm going to do, I'm going to implement O gate using NOR gate. Now to implement NOR gate using O gate using NOR gate, we have to use first of all NOR gate. We know NOR gate is something like this. We have O, O gate, and this is NOR gate. So inputs are, we can say like this. We can say we have A, we have B. So we will have the outcome. So this outcome will be A dot B bar, isn't it? Sorry, A plus A bar. A plus B bar. What we need is A plus B. That means we need a NOT gate. So to get a NOT gate, what we do, we add another NOR gate like this. And this, let me say F. The inputs are, we short circuit. That means we are input same, right? And we'll get F. So now, if you look at the outcomes, so we have AB here. So that means we'll get A plus B bar. So we'll get A plus B bar, A plus B bar, bar. So F will be A plus B bar, right? Plus A plus B bar. And then you have to take the whole bar. So this is the output. So now, if you take the truth table, now to understand this, let's take a truth table. So to have the truth table, we need both A and B. So we need A plus B. Let's directly take A, B bar. And then we can say A plus B bar into, sorry, plus A plus B bar. And finally, we can say F is actually complement of this. So if you do this, right? So we can take the values. So we know A should be 0, 0, 0, 1, 1, 0, and 1, 1. So addition and bar. So you add 0 plus 0, 0, bar is 1. You add 0 plus 1 is 1, bar is 0. 1 plus 0 is 1, bar is 0. 1 plus 1 is 1, bar is 0. So this is how we will get. And then you are going to add the same thing. 1 plus 1, this is 1. 0 plus 0, 0, 0, 0. No change. Then to get F, you know that you have to get the complement of this. That means this is 0, 1, 1, 1. Which means this is similar to no gate. Right? So this is similar to no gate. Sorry, O gate. We can say this is similar to O gate. We have O gate. If this is F or Q, earlier we have used Q, right? So better we use Q here as well then. Here, so this is Q. We have A, B inputs. So when you have A, B, so we know Q is A plus B. So if you take the truth table, we have 0, 0, 0, 1, 1, 0, 1, 1. Addition means 0, 1, 1, 1, which is similar. So we can say that these two circuits are identical to each other, right? This is identical to each other. So let's write down the new part which we are going to discuss today. That is, we are going to talk about how we can simplify logic expressions. So let's write down. Simplify logic expressions using laws of Boolean and Carnot maps. Right. So in this part, we are going to look at simplifying logic circuits. Now, for example, from the previous simplification, you might see that you can have a simple circuits, right? So we start with the original logic and then we will simplify. අපි මොන හරි සර්කිට් එකක් හදනකොට ඒකට ඕන මූලික සර්කිට් එක අපි හදනවා. ඒක ගොඩක් වෙලාවට ටිකක් සංකීර්ණ එකක් හම්බෙන්නේ. අපි ඊට පස්සේ ඒක සිම්ප්ලිෆයි සරල කරගන්නවා ඉම්ප්ලිමන්ට් කරන්න කලින්. We can save lot of gates. The cost can be reduced. Right. So when we design logic gates, we can simplify this using some laws. In mathematics also, sometimes you know uh, uh, when you have expression, you learn how to simplify this. Um, let's write down under this. When building circuits, the cost can be reduced if the number of kits used can be reduced. So when you're building a circuit, the number of logic circuits, if you can reduce, then cost will be reduced. Using Boolean algebra or Carnot maps. I will explain what the Carnot maps are. We can simplify the complex circuit into a simple circuit. Right. Very complex circuit, we can make it simple using the two techniques that we are going to discuss now. There are some advantages of this. Let's discuss the advantages. There are a couple of advantages. One thing is the circuit design will be simple, right? So we can say circuit design will be simple. We can say circuit. These will first of all say advantages. We will say simple is. You will have simple circuit designs. Low cost of manufacturing. So since you are going to reduce the number of cakes, right, the cost will be low. First of all, let's look at laws of Boolean algebra. So I'm going to start the first part. We'll introduce first how we can simplify the circuits using laws of Boolean algebra. Right. So we are going to write down a couple of algebraic equations and we will discuss their proof as well. So let's start with the first commutative loop, right? Write down the first one. We'll start with the this. The first one will start with like this. We'll start with idempotent loop. Idempotent loop. Should be idempotent. Low means LAW. Right. Now, idempotent means we are going to talk about a couple of things, right? That means if you use the same variable for multiplication and addition, you'll get the same answer, right? So that's idempotent. Now let's start the first one. Let me take first law is, we can say A dot A is A. So this is one representation. Similarly, we can write couple of more like this. For example, right? So this is one, and we can say A plus A, that is also A. This is also A. Can you draw the truth table and verify this? And similarly, we can also get complements. When you have A bar here, A bar should be A bar. Similarly, A bar plus A bar should be A bar. Right. So here are the four rules with idempotent loop. So A dot A, that means Boolean multiplication with the same variable, you get the same variable. Boolean addition, that means OK, you will get the same. If you have complement A bar, so you will get A bar. And complement of addition, you will get A bar. So these are the four things. Right. If you want, you can simply write a truth table. For example, we can have A, then we can have A dot A, which will be similar, isn't it? So here also, we can have A, then we can have A plus A. Similarly, A, we can have A bar, then we can have A bar dot A bar. Similarly, we have A bar plus A bar. We can draw two tables like this. So here is the first one. You can fill the table. Fill the table. So here also we can fill the table and observe whether we are getting the same answer. Here we will get A, and then we get A bar, and then we will multiply A bar with A bar. Check the answer. Similarly, here also we have A, we have A bar, then you add A bar plus A bar. Let's look at the answers. We know that here you have only one variable, that is A. So when you have one variable A, the inputs are 0 and 1. So 0 dot 0, that means when you multiply 0 with 0, this is 0. 1 with 1, this is 1. Similarly, here as well, we have 0 and 1. So we have 0 plus 0, that is 0. 1 plus 1, this is 1. Similarly, here we have 0 and 1. So we know the complement will be then 1 and 0. And 1 into 1, this is 1. 0 into 0, this is 0. So we will see that A dot A bar dot A bar is equal to A bar. So this is also the same. And similarly here, when you have 0 and 1, we have 1 and 0 here, right? So 1 plus 1, this is 1, 0 plus 0, that is 0. So you can see that, yes, these identities are there. For example, when you want to simplify something, if you have the same variable again and again, you can, instead of 2, you can make it a 1. Now, for example, if you have like A plus B into A plus B, we know we can simplify into A plus B, right? So that's how we are going to handle it, right? Then we have what we have identity loop, the second one, right? So let's write down second one, identity. Right, here also a couple of expressions. You can try the same. So whenever you multiply this with one variable, this law says it's 1. So 1 dot A equals 1, sorry, equals 1. Sorry, equals A. Sorry. Because when you multiply with 0, 1 into 0, you will get 0, 1 into 1, you will get 1, which means 1 into A is A, right? So this is 1. Second one, when you have 0 plus A, this will be A, no change. Similarly, 0 multiplied by A will be 0. Just check. 1 plus A equals 1. Right? So similar to the previous one, I want you to draw truth tables and send it to me. Draw the truth table and send it to me. Right. Now, to draw the truth table, we can have a couple of things. We can have 1. We can have 1. We can have A. Then we have 1 dot A. Similarly here, we have 0. We have A. Then we have 0 plus A. And the next one, we have 0. Then we have A. Then we have C, multiplication of 0 and A. Now here we have 1. We have A. We can have 1 plus A. Right. So let's draw the truth tables. That is the first one. We have 1 and A. What is 1 plus A? Here we have 0. A. What is 0 plus A? Here we have 0. A. What is 0 multiplied by A? Here is we have 1. A. We need 1 plus A. So now if you put the values, just put the values here. A, we know that we will have 0 and 1. So this is 1 and 1, right? 1 is same. So now just multiply and see what is the outcome you are getting. Similar to here we have 0. Here we have a 0, we have 1. So here we have 0, 0, 0, 1. So here 1, 1, we have 0. Just fill the table and send to me with you. Let's put the answers. When you have 1, multiply with the Boolean variable A, no change of the variable, which means you will get the same outcome when you multiply these two. So this will be 0 and this will be 1, which is similar to A. So this is true. Then addition of 0 with a Boolean variable. So no change of the variable, because whenever you add a 0, won't change the original outcome. 0 plus 0 is 0, 0 plus 1 is 1. Then multiplication of any Boolean variable with 0. So this will give you output. 0 into 0 is 0. 0 and 1 is 0. Then we have 1 plus A. So whatever we have A, when you add 1, you will get the outcome as 1, isn't it? So 1 plus 0, this is 1. 1 plus 1 is 1. So these are the things that you need to comes under identity loop. Right. The next one we discuss is called inverse or complement loop. Inverse or complement loop. So let's move to the third one. Third loop. We can say inverse or complement. Right. There are two forms of this. Right. Two forms. First of all, we call under this one, we say multiplication form. Multiplicative form. So what this means, the rule says when you have a variable and when you multiply its complement, you'll get 0. Right? So idea of this is if you take a variable and if you multiply with its complement, it says you are getting 0. So draw the truth table. Similarly, there's another form. So this form is called additive form. So in additive form, we can have A plus A bar equals, it says 1. So that means here it says when you take a variable and if you add the complement, you always get 1. Right. Can you draw a truth table? For these two and share with me? So let's write down the fourth law, a very important one. This is called De Morgan's law. De Morgan's law. So there are two forms on De Morgan's law, right? Like in previous case. So the first one it says, so the first one we have multiplicative form. So that is, we say A dot B total bar is equal to A bar dot B bar, right? So this is what we call we have A dot B bar, it's equal to, sorry, this should be plus. That's my mistake. Right, so this is equals to A bar plus B bar, right? Now let's try to prove this. Now, to prove this, we have to tell that A, we have to have B, then we have to have A dot B, then we have A dot B bar, then A bar, then B bar, then A plus B bar. Right. I think this is enough for us, right? AB, we have AB and AB bar. So this is this one. Then we have A bar, we have B bar, and this A bar plus B bar. So ideally, we should get same answer in, let me put the values, 2 columns. That means this column and the last column. The value should be same. So let's put some values. So we have 0, 0, we have 0, 1, 1, 0, 1, 1. Yes. Can you complete the table and send it to me? So in this part, we are going to look at the second form of De Morgan's law, which is additive form. In additive form, we will have A plus B bar equals A bar dot B bar. So if you look at carefully both forms, if you replace dot operator with plus and plus with dot, you will get the same. So let's draw an truth table and see whether you are going to get the same identity. Start with, we can have A, then B, we can have A plus B, and then we have A plus B bar, right? Then we can have A bar, B bar, A bar dot B bar. Those are the things that we need. We have A, B, then A plus B bar, then A bar, B bar, then we have A bar dot B bar. So we have A, B, A plus B, A plus B bar, A bar, B bar. Okay, we have A dot B. So if you look at the same, you should see that this column should same for this column if you have done it correctly. So the fifth law is called double complement law. So double complement means Yes, you have double bar. You add not operation twice. The idea is you will get the same answer, right? So draw the truth table. Now to simplify the truth table, you can have A, then you can A bar and A double bar, right? You are applying not twice. So that's the idea. So in this one, we can say, usually we know that we have two. Binary means we have two. So that is 0 and 1. So first complement, whenever 0, this becomes 1. Whenever this 1, this is 0. Again complement. So 1 is 0, right? 0 is 1, which is equal to each other. A and A double bar the same. The sixth one we call commutatively low. That means when you perform some operation, we say order doesn't import, right? Again, there are two forms. We have multiplicative form, which means we are going to say here A dot B is equal to B dot A. Now, similarly, the other form, we have additive form, which means when you have A plus B will be the same as B plus A. So we can say that we can have, to draw the truth table, we can have B, then we can have A dot B, and we can have B dot. The next one also you can do the same. We can have AB. The next form is we can have A, B, A plus B, then we have B plus A. Okay, so let's draw the truth table and send it to me. Yes, truth table will be similar to this. Draw the truth table for both and share with me. It's the seventh one. Now, seventh one, again, there are two forms. We call associative loop, right? So let's write down associative loop. The seventh one we call associative loop, which means we have two forms. So what multiplicative form means, if you have like variables, three variables, let's say A dot, let's say B dot C. Now, when you want to multiply, you can say you can first multiply BC and then A. Similarly, you can change the order here. If you multiply first with A, then with C, you are getting the same answer. Now, to understand this, we again have to draw a truth table. So we have to have A, B, and C, right? And then the multiplication. So that means, first of all, B dot C. Now, then we have to say A dot, right? B dot C.